What's up? And we are continuing with related rates. Again, now we're going to talk about a couple more complicated problems. Right, so in our first one, we have water running out of a conical tank, so a cone, at a constant rate of 2 cubic feet per minute. The radius at the top of the tank is 5, the height of the tank is 10. How fast is the water sinking when the water is 4 feet deep? Right, so first I'm going to make a list of information that I know. Okay, I know that the volume is changing at a rate of 2 cubic feet per minute, right? So I know that dV dt is changing. Now, water is leaking out of the tank. Okay, so my water volume is decreasing, meaning that my derivative will be negative, right? So I know that it's negative 2 feet cubed per minute. Okay, I know that the radius at the top of the tank is 5. And the height is 10. All right, now there's some very specific things that we got to do with that, but for now I'm just going to write it down. Okay, and then it's asking me how fast the water level is sinking when the water is 4 feet deep. So when it says how fast is the water level sinking, really that's going to be the height. So that's going to be dh dt when specifically the height is 4 feet. All right, so it might help to draw a picture. So let's draw a picture real quick. Let's draw right here. All right, so here's my tank. Here's my tank. All right, I know that I have a radius of 5 and a height of 10 feet. Okay, and also I know that there's water in my tank. Okay, that was the worst thing ever. Hold on. Okay, there's water in my tank, and water is coming out. And so this height right here, I know is decreasing. So specifically, when this height is 4, I want to know how fast the height is changing. Right, and as you can see, the height will be changing at a different rate as the water increases or decreases because it's a cone. Right, so that's what I know, and I know that the volume is decreasing at a rate of negative 2 feet cubed per minute. Okay, so let's talk about what to actually do with some of this information. This is very important here. So I know that the overall size of my whole tank is has a radius of 5 and I have a height of 10. So what that tells me is that my radius to height ratio is 1/2, meaning that my radius is always going to be 1/2 of my height. Okay, so in any cone, this is something that you're going to have to remember. For any given cone, the ratio between the radius and the height will remain constant. For any cone, any problem, not just this problem, any problem, the the ratio between the radius and the height remains constant. In this particular cone, the ratio between the radius and the height is 1 to 2. Okay, that's specific to this problem. The ratio is 1 to 2, meaning that the radius will always be half of my height. That's what I know. The reason why this is important is because they didn't tell me the radius when the height is 4. And that's the information I actually need. I don't really need to know the dimensions of the overall tank because I'm not really concerned with that. I'm concerned about the height of the water, not the height of the overall tank. So I need to know the radius of the water level as well, or I need to know the radius of the circle that the water makes when the height is 4. And they didn't tell me that, but I can find out very easily. When I plug in 4, I know that my radius is going to be 2 because the ratio between the radius and the height is always constant. Okay, so at this specific point in time, I know that my height is 4 and my radius is 2 feet. That's what I know. So now I can go ahead and try to get some stuff done. So I'm relating volume to radius and height. So I'm going to write down my volume equation. The volume of a cone is 1/3 pi r squared h. All right. And before we take the derivative, first of all, consider what you'll get. Okay, if I take the derivative here, I'll get a dv dt over here. I'll have to do product rule, but in the end, I'll end up with a dh dt, and a dr dt. Okay, meaning I'll have to end up plugging in values for how the height is changing over time and how the radius is changing over time. I have no information on how the radius is changing over time. In fact, it's going to be it's just, there's not much that I can do about that. So it would be smart to substitute r out of my equation. Okay, and I can do that because I know something about the radius. I know that the radius is always half of my height. Okay, I do not know how the radius is changing over time, but I know that at any time my radius will be half of my height. This is something I can generally use for this problem. So I can substitute. Okay, so all I did was I substituted 1/2 h in for r. All right, let's simplify this just a little bit. So I get 1/4 times 1/3 is 1/12 pi. And then h squared times h is h cubed. All right, so this is the volume equation that I'm going to be working with. So now when I take the derivative, so let's take the derivative of the whole thing. I'm taking the derivative with respect to time. Okay, the derivative of v is going to be dv dt. And here I don't have to do any product rule or anything because pi over 12 is just a constant. So the pi over 12 is just going to chill. And the derivative of h cubed is going to be 3h squared dh dt. Okay, now I can plug in what I know. Right, so I know that dv dt is -2. You know what, I'm going to go ahead and include my units, feet cubed per minute. And that's equal to, okay, pi over 12 is a constant. You know what, let's simplify this to pi over 4. We'll get rid of that 3. So pi over 4, I know h is 4 feet. That's being squared. And then dh dt is what I'm trying to figure out. And the reason why I'm including my units in this example is because it makes it really easy to figure out what your units are for your final answer. Okay, so let's simplify this mess just a little bit. I have -2 feet cubed per minute equals to, these 4's will kind of cancel, so I'll end up having 4 pi feet cubed times dh dt. Okay, so now let's divide. So let's divide everything by 4 pi feet squared. Okay, so I'm solving for a dh dt. So -2 over 4 pi is going to be just -1 over 2 pi, which is fine. Okay, and then I got feet cubed divided by feet squared. So that's just going to end up being feet. Right, and that's why I included my units here. It made it really clear what my end units should be, and you will get deducted on the AP test if you do not include your units. So make sure you include those. Okay, nothing with minutes was ever over here, so minutes stays exactly the way it is. But feet cubed divided by feet squared is just feet. Right, so this is my final answer. I find that my height is decreasing at a rate of 1 over 2 pi feet per minute. Or you could say it's changing at a rate of -1 over 2 pi feet per minute. Okay, let's keep going. One more example. All right, I got a dude, he's 6 feet tall, walking at a rate of 5 feet per second towards a light pole. And I want to know a couple things about him. All right, so let's start with part A. All right, first I want to know at what rate is the tip of his shadow moving when he is 10 feet from the base of the light. Okay, so kind of complicated. There's a lot of things going on here. The general idea is this is my pole. This is my light source, right? And so if my light source is hitting the top of the dude and it continues, right, then here is his shadow. So this is his shadow. This is the distance between him and the pole. And so I'm going to label my diagram very specifically, right? I know that this is 16. I know this is 6. And I'm going to label this entire length here X. All right, and I'm going to label the distance between the man and the pole y. All right, so again, I labeled the entire distance, so from the pole to his shadow, to the tip of his shadow, I labeled that x, and the distance between the pole and the man, I labeled y. That means that the distance between the man and his shadow, or the tip of his shadow, is x minus y, right? So total distance minus this little bit over here. So the distance between the man and the tip of the shadow is x minus y. Okay, that's how I labeled this. And if you'll notice, I have a bigger triangle and I have a smaller triangle within. We can use similar triangles here. So think back, way back to geometry. Okay, I know some things about the ratio of the sides. Okay, I know that this side and this side are proportionate to this side to this side. Okay, so I'm going to make a simple proportion. I know 16 is to x, so the length of my bigger triangle, and I know they're equal in proportion to 6 over x minus y. Right, they're equal in proportion to 6 over x minus y. All right, so I made my proportion. Now, again, like I said before, I like to make a list of everything that I know. So let's see what I got. Okay, I know that he's walking at a rate of 5 feet per second toward a light pole. Okay, so I know that my distance here is, we can say it's decreasing. Okay, and I know that dy dt is -5. Okay, so basically what I'm saying here is my distance between the man and the light pole I called y. Okay, and I know that y is changing at a rate of 5 feet per second. He's walking towards the light pole, so I know that y, which is this distance right here, is decreasing. So I know that dy dt has to be negative, and I know that it's 5 feet per second. Okay, that's something that I know. And the question is asking me at what rate is the tip of his shadow moving when he is 10 feet from the base of the light? Okay, so he's 10 feet from the base of the light. That means that this distance right here, my y distance, is 10 feet. And I want to know how his shadow is moving. And the distance between the pole and his shadow is x. So I'm trying to figure out what dx dt is. Okay, so just a quick review. The distance between the pole and the man is y, and that at this split second in time, that is 10 feet. I know that this distance is changing at a rate of 5 feet per second, negative 5 feet per second, I should say. It's decreasing, and I'm trying to find this how this total distance here is changing. Okay, the tip of his shadow, how the tip of his shadow is moving. So I'm trying to figure out how this whole distance here is changing. Okay, so now let's simplify my proportion. So I have an equation here. Now I know some information. I specified what I know, and I specified what I'm trying to find. So let's cross multiply. So I get that 16x minus 16y is equal to 6x. Okay, so now let's get all the x's and y's separate from one another. I know 10x is equal to 16y. So I know x equals, let's simplify it a little bit, 8/5 y. And the reason why I solved for x here is because I'm trying to find dx dt. All right, so now when I take the derivative, so I'm taking the derivative with respect to time, I get that dx dt is equal to 8/5 dy dt. The derivative of y with respect to t is just dy dt. All right, now let's plug in what I know. I know that dy dt is -5. And so these end up canceling out. I end up getting -8, sorry. -8, and dx dt is going to be in terms of feet per second. All right, and it makes sense that it's negative because I know that this distance should be decreasing. So I know that my total length here is decreasing at a rate of 8 feet per second. Or you could say it's changing at a rate of -8 feet per second. All right, let's move on to part B. Part B wants to know what rate is the length of a shadow moving when he's 10 feet from the base of the light. So this is different from part A in that part A wanted to know at what rate was the tip of his shadow moving. So it wanted to know how this like whole distance was changing, basically. Part B wants to know at what rate is the whole length of his shadow moving. So we want to know how this distance right here, just his shadow, is changing. That's what I want to know. So I'm going to rename my triangle here just in a couple ways. Okay, I'm going to define my shadow as x. I'm going to define my shadow as x because that's what okay, that's just ugly. As x because that's what I'm going to end up trying to find. I want to know how his shadow is changing over time. I'm going to end up solving for dx dt. So I'm going to call this x. I'm going to call the distance between him and the pole y, meaning that this total distance here is x plus y. Okay. We're going to approach this the same way that we approached part A. So I'm going to create a ratio because I have similar triangles. All right, so 16 is to x plus y as 6 is to x. And again, the reason why it was so important for me to label this x, so renaming it from part A, is because part A I had multiple variables here. In part B, I'm trying to figure out how this distance is changing. So I just wanted a single variable there. All right, so what we know doesn't really change. Okay, I know that it's specifically when he's 10 feet from the base of the light, so I know y equals 10. Okay, I know that he's still walking towards the light pole, so I know that dy dt is still negative 5 feet per second. But this time I'm trying to find a different dx dt. Okay, this dx dt I'm finding is specific to right here. It's not the whole thing, it's specific to right here. I should get a different answer from part A, even though the information I wrote looks the same. Okay, so let's cross multiply. I get 16x is equal to 6x plus 6y. Right, and so let's get x by itself. I get 10x is equal to 6y, so x is equal to 3/5 y. Okay, now I'm ready to take the derivative. So I end up getting that dx dt is equal to 3/5 times dy dt. Okay, so again, dx dt is what I'm trying to find. I know that dy dt is negative 5. Okay, so the 5's here cancel. I end up getting that my dx dt is negative 3 feet per second. And that's my final answer. Okay, so this whole shadow is moving at a rate of negative 3 feet per second. It's approaching the pole at a rate of 3 feet per second. Right, now you'll notice that we didn't end up using this value right here. I didn't end up using that y equals 10. That's why it's so important to remember not to plug any numbers in until you take the derivative first. Okay, so we couldn't plug this number in because I know that his distance is changing. I know that this distance is changing right here. So I couldn't plug it in before. And then it turns out after I take the derivative that I didn't even need this information. Okay, so it's very important to remember to take the derivative and then plug in your values. And really, you got to know what's changing and what's remaining constant in order to be able to make that determination. Okay, but we didn't end up needing this. It was extraneous information. Right, just a note. That'll happen sometimes. Okay, so I get this situation here, and that's all that I was asked to do. So we're done. I'll see you all later.